In the autumn of 1725, inside a house in Kew, two men were waiting for a star to move. James Bradley and Samuel Molyneux had fixed a telescope so carefully that even the smallest change in a star's position might reveal something generations of astronomers had longed to see. If Earth truly traveled around the sun, then the stars should seem to shift just a little over the course of a year. It was an idea simple enough to describe in a sentence, and yet for centuries it had resisted every attempt to turn it into visible proof. Night after night, the instrument pointed upward, and the sky answered in a language that was almost too quiet to hear. Picture the scene for a moment. A narrow beam of attention, a patient eye, a room arranged around precision, and above it all, a universe that appears perfectly still. This was the strange difficulty at the heart of one of the greatest scientific questions ever asked. Earth moves, and yet nothing in ordinary experience seems to confess it. The ground beneath your feet does not tremble with speed. The air does not tear past your face. The stars do not obviously slide across the heavens as the months go by. For a very long time, the deepest argument against a moving Earth was not theology or tradition, but the stubborn testimony of the senses. And yet the idea would not go away. Copernicus rearranged the cosmos with a daring elegance that placed the sun at the center and set Earth in motion. Galileo turned his telescope upward and found a sky far less obedient than the old world had promised. Kepler and Newton transformed celestial order into something dynamic and intelligible. Again and again, the case for Earth's motion grew stronger, and yet the final certainty seemed to retreat just ahead of reach, as if nature were willing to suggest the truth, but not surrender it all at once. This is the story of that long pursuit. It is a story about evidence that arrived late, about objections that were more intelligent than we often remember, and about a fact so enormous that humanity needed centuries to truly secure it. How do you prove that the world beneath you is moving when it feels so completely still? And what does it mean that one of the most important truths in science had to be uncovered by learning, little by little, not to trust the silence of the earth? Step outside on a clear night, far enough from the noise of traffic and the glow of windows, and for a moment, the world seems to return to an older scale. The ground beneath you feels firm, settled, perfectly at rest. Trees stand in dark outline. Air touches the skin so lightly that it almost disappears. Above, the sky seems alive with motion. Stars drift slowly from east to west. Constellations climb, lean, and descend. The moon crosses from one part of the darkness to another, and if you stay long enough, even the blackness itself seems to turn like a great roof. Almost everything in the scene suggests movement, but not the thing you are standing on. The earth does not announce itself as a body in motion. It feels like the still point from which motion is measured. That impression is so deep that it does not merely belong to astronomy. It belongs to the body. When people say the earth moves, they are speaking against something that seems almost more intimate than belief. They are speaking against balance, against the quiet reliability of standing upright, against the ordinary trust that falling water falls straight down, that smoke rises into the same sky each day, that a dropped stone returns to the ground beneath the hand that released it. Nothing in immediate experience suggests that the solid world is racing through space. Nothing in the ordinary rhythm of walking, sleeping, farming, building, or watching the weather makes it easy to imagine that the surface under every city and field is rotating. and at the same time circling the sun at tremendous speed. Long before the question became mathematical, it was physical in the simplest human sense. The earth felt still. That feeling mattered more than modern imagination often allows. It is easy now, when the motion of the earth is taught in childhood, to look backward and wonder how anyone could ever have believed otherwise. But to understand the long search that would eventually prove Earth moves, it is necessary to linger inside the older certainty and feel its force from within. The sky seems to move because the sky is what changes. Dawn arrives from one horizon and leaves at the other. The sun arcs overhead. The stars circle around the pole. Seasons alter the height of the sun and the length of shadows. But even those changes suggest a heaven in motion above a waiting world below. If you had no telescope, no modern physics, no idea of inertia, and no reason to distrust the evidence of the senses, the simplest reading of the world would not be that Earth moves and the heavens only appear to move. It would be the reverse. Ancient natural philosophy did not build that conclusion out of mere stubbornness. It grew within a wider attempt to make the visible world coherent. In the Aristotelian picture that came to dominate educated thought for centuries, the earth belonged at the center of the cosmos because heaviness itself seemed to point inward. Stones fell toward the middle. Soil and water sought their natural place below air and fire. Up and down were not just directions, they were part of the structure of reality. A heavy, central earth was not simply one object among others. It was the place toward which earthly things tended. Above the changing world of growth, decay, weather, and death lay the heavens, more orderly and more perfect, moving in continuous circles. Motion in the sky and rest at the center formed a pair that seemed to answer to experience, logic, and metaphysical taste all at once. The cosmos, in that view, was not arbitrary. It had character. This older world could also be calculated. Greek astronomers, and later astronomers working in the Roman, Islamic, and medieval Christian worlds, developed increasingly sophisticated ways of describing celestial motions while keeping the earth fixed. The most influential of these systems, associated above all with Claudius Ptolemy, was not a simple children's picture of circles around a motionless world. It was a mathematically intricate machine of deference, epicycles, offsets, and corrections, designed to match what observers actually saw. Its importance lay partly in a fact that deserves respect. It worked well enough to be useful. It could predict planetary positions with serious technical skill. Calendar making, astrology, religious observance, and scholarly astronomy all lived inside a framework that was not merely inherited, but constantly used. The fixed earth was not only intuitive, it was woven into a functioning intellectual tradition by the Middle Ages. This vision of a central earth below the turning heavens had become more than a scientific model. It was a habitat of thought. Universities taught it. Commentators refined it. Theologians often accommodated it, not because Scripture alone demanded it, but because it fit so naturally with the philosophical structure inherited from antiquity. The everyday and the cosmic appeared to support one another. The human world was a world of weight, friction, decay, and downward motion. The celestial world was regular, elevated, and cyclical, looking upward at the nightly wheel of stars. Many educated observers felt they were seeing not confusion, but order. The earth beneath them seemed as stable as the foundations of a cathedral. the sky above them seemed as precise as a clock. If the cosmos had a grammar, this was how it read. And yet the strength of that grammar lay not only in habit, but in objection. A moving Earth did not simply sound strange. It sounded physically troublesome. If the Earth rotated, why were people not hurled westward? Why did birds return to their nests instead of being left behind by a rapidly turning ground? Why did clouds not stream endlessly in one direction? Why did objects drop from towers, not fall far from their base? A world in motion should leave traces of that motion. And to older thinkers, those traces seemed absent. The objections were sometimes framed differently in different ages. But the core intuition remained the same. Motion ought to show itself. If something immense is moving, especially moving quickly, one expects consequences that can be seen and felt. Stillness may be deceptive in some situations, but could it really deceive on the scale of the entire Earth? Even more powerful was the problem of the stars. If the Earth traveled around the sun over the course of a year, then the stars should not appear in exactly the same places from month to month when observed against one another. Nearby stars should seem to shift slightly as the observer changes position, just as a nearer object shifts against a distant background when viewed first from one side of a road and then the other. This effect, which later astronomers would call parallax, seems modest when explained now. But in the older debate, it carried enormous weight. If Earth moved through a vast yearly circuit, the heavens should quietly betray that motion. Yet no such shift could be seen with the naked eye. The constellations returned in season. The bright stars held their patterns, and the sky offered no obvious sign that the observer had been carried to a new place in space. This absence was not a trivial inconvenience. It was one of the strongest reasons to doubt the Earth's motion at all. To feel the full force of that difficulty, imagine watching the same stars in winter and then, again, many months later, expecting some minute rearrangement, some faint confession that your world has changed position. Instead, the shapes hold. Orion remains Orion. The familiar bright points come back with the seasons, and their relationships seem undisturbed. The sky does change, but not in the needed way. For centuries, this was devastatingly persuasive. Either the Earth did not move, or the stars were so far away that their shifts were too small to detect. That second possibility would eventually become essential, but for a long time, it felt almost absurd to save a moving Earth. The universe itself had to become unimaginably larger than many had supposed. A theory that demanded such distances could easily seem like an escape rather than an answer. There were, it is true, moments of early speculation that cut against the common picture. In the ancient Greek world, a few thinkers entertained alternatives to the standard arrangement, and Aristarchus of Samos is remembered for proposing a sun-centered cosmos centuries before Copernicus. But these ideas did not reshape the intellectual world around them. They lacked the observational success, physical framework, and institutional momentum needed to overturn the dominant view. That is an important lesson, and a humbling one. History does not move forward simply because a true idea appears. An idea can be brilliantly correct and still remain weak if the surrounding evidence, tools, and concepts are not ready to sustain it. The older Earth stayed in place not because nobody had ever imagined otherwise, but because the alternative could not yet carry enough weight. What held the fixed Earth in place, then, was not one argument but a whole atmosphere of plausibility. The body seemed to confirm it. The eye seemed to confirm it. Motion in the heavens seemed daily and obvious, while motion in the Earth seemed absent and even contradictory to experience. Philosophy supported it. Mathematics accommodated it. And ordinary language quietly reinforced it. We still speak today in ways shaped by that old intuition. The sun rises. The sun sets. The stars wheel overhead. Language preserves what the senses first report. And for much of human history, that report sounded not naive, but true. Even now, stripped of theory, the immediate world still presents itself this way. The stillness that once anchored the geocentric cosmos has not disappeared. It has merely been reinterpreted. That reinterpretation would take far more than a single bold thinker. It would require people willing to distrust first appearances without becoming careless about evidence. It would require new mathematics, new instruments, new ideas about motion itself. It would require a slow separation between how motion feels and how motion actually works. But before any of that could happen, there had to be a period in which the old stillness remained persuasive enough to resist every premature victory. This is part of what makes the history so rich. The earth was not waiting to be discovered as moving by minds too enlightened to be fooled. It was hidden in plain sight by the very stability of daily life. The fact that the truth could remain concealed inside such familiarity is one of the most unsettling things in the history of science. There is also a psychological depth to this resistance that is easy to miss if the story is told too quickly. A fixed earth did not only explain the world, it offered orientation. To live on a stable ground beneath a moving heaven is to inhabit a cosmos that seems arranged around a center. Remove that stillness, and something more than astronomy begins to shift. The earth becomes a body among bodies, not the unmoving stage on which celestial motion is displayed. Human beings become passengers without feeling themselves to be in transit. Home becomes dynamic. Rest becomes relative. Even before such ideas were philosophically digested, there was a quiet estrangement waiting inside them. A moving earth was not only a technical claim, it altered the emotional geometry of the world. And so, when later generations began to reopen the question, they were not stepping into empty space. They were stepping into a carefully built world whose confidence came from everywhere at once. They were facing a universe in which the senses, the schools, the inherited authorities, and the stars themselves all seemed to say the same thing. That is why the eventual reversal would be so difficult, and why it could not be accomplished by elegance alone. To move the earth, one first had to loosen the grip of the obvious. One had to make it imaginable that the deepest stillness in human experience might be, in part, an illusion. In the early 16th century, that is precisely what one quiet scholar would dare to do. He would not begin by proving the earth moved. He would begin by rearranging the heavens with such strange simplicity that the old certainty could no longer rest as comfortably as before. In the early 16th century, the old stillness did not collapse all at once. It was approached quietly, almost from the side, by a man who spent much of his life far from the image that later centuries would build around him. Nicholas Copernicus was not a wandering rebel standing outside the learned world. He was deeply inside it. He had studied in Krakow, then in the university culture of Italy, where astronomy, mathematics, medicine, law, and classical learning overlapped in complicated ways. He returned to the lands of Royal Prussia, within the Kingdom of Poland, and lived much of his adult life as a cathedral canon at Frombork, involved in administration, finance, legal disputes, medical service, and the quiet burdens of ecclesiastical life. If one imagines the man who displaced the Earth, it is easy to picture an isolated visionary gazing upward in permanent defiance. The reality is stranger and more human. The mind that proposed a moving Earth belonged to someone woven into everyday responsibilities, riding between obligations, working in relative isolation, and carrying an idea whose full consequences even he moved toward with caution. There is something fitting in that slowness. The older cosmos had not been built in a year, and it would not be overturned by haste. Copernicus inherited a learned astronomy that could calculate planetary motions, yet often did so through devices that felt mathematically effective without being fully satisfying in form. To later eyes, the Ptolemaic system can look baroque, a maze of circles built to rescue appearances. But Copernicus did not reject it simply because it was old, nor because he sought novelty for its own sake. He was troubled by the lack of harmony he felt in the inherited arrangement. The sky, if it reflected divine order, ought to be intelligible with a deeper elegance than the patched complexity he believed he had received. This is one of the subtler psychological threads in his work. He was not chasing proof in the modern experimental sense. He was searching for a cosmos that fit together more beautifully, more coherently, more like a whole. That search began to take shape years before the world saw the great book that would carry his name. Sometime around the early 1510s, Copernicus drafted a short manuscript now known as the Commentariolus. It circulated only in limited form, hand to hand, among a small number of learned readers. In it, the central rearrangement was already present. The sun was placed near the center. The Earth was no longer the unmoving middle of everything, but a planet with motions of its own. Daily rotation could account for the rising and setting of the heavens. The yearly journey of Earth around the sun could explain the apparent motion of the sun through the zodiac and shed new light on the behavior of the planets. Retrograde motion, that strange backward wandering of Mars, Jupiter, and Saturn against the stars, no longer needed to be treated as a peculiar trick performed by the planets themselves. It could arise naturally from the fact that an observer on a moving Earth sees other planets from a changing vantage point. To feel the quiet force of this proposal, picture the night sky as people had long known it. Certain planets sometimes slowed, stopped, and drifted backward for a time before resuming their usual path. In the older mathematical systems, these motions could be represented, but they had to be built into the machinery by carefully layered circles. Copernicus offered something different. The strange path remained in the sky, but its meaning changed. Some of the disorder was no longer in the planets. It was in the observer. Earth itself had joined the dance. Once that move was made, a scattered set of celestial oddities began to look more like the optical consequences of sharing motion with the other worlds. This was the beauty of heliocentrism in its early form. It did not simply replace one central object with another. It transformed appearance into perspective. That change, however, was not the same thing as proof. Copernicus could offer a more unified arrangement of the planetary system, but the old questions from lived experience remained waiting below. Nothing in his model made the ground feel less stable underfoot. Nothing in it caused the stars to exhibit the missing parallax that critics would continue to demand. If Earth moved, then motion itself had to be understood differently than common sense suggested. Yet, Copernicus did not possess the later physics that would make such claims easier to inhabit. His system was mathematically and conceptually alluring, but it did not yet close the gap between elegant order and physical certainty. It asked the learned world to accept a more daring interpretation of the heavens before nature had supplied an obvious confession. This is part of what made the idea so difficult to classify. Was heliocentrism a true description of the cosmos, or a useful computational fiction? That question would remain entangled with the book that eventually emerged. And it reveals a good deal about the intellectual atmosphere of the time. In the 16th century, astronomy and natural philosophy did not always ask the same thing of a model. Astronomers might seek accurate predictions. Philosophers might ask what the heavens were actually like. A system that saved the appearances could be prized without necessarily being treated as physically real. Copernicus himself plainly leaned beyond mere convenience. He believed his arrangement expressed something about the true structure of the world. Yet the culture that received him had room for ambiguity. And that ambiguity would become one of the first shelters in which the new system survived. Years passed. The short manuscript did not become a printed revolution. Copernicus kept working. He refined numbers, revised geometric constructions, and deepened the architecture of the system that would eventually become De Revolutionibus Orbium Coelestium. The revolutions of the heavenly spheres. The delay has invited many interpretations. Later legend often preferred dramatic explanations, especially the image of a thinker held back by fear of religious persecution. Historians have been more careful. There is little reason to reduce the long hesitation to a single cause. Copernicus was meticulous. He was burdened with other duties. His observing circumstances were modest, and his standards for completion appear to have been high. He seems to have been wary of exposing an unfinished or insufficiently grounded system to a learned world that would scrutinize it closely. Caution, in his case, was probably temperamental as much as strategic. That caution can feel almost built into the book itself. Copernicus was not a great stylist of controversy. He did not rush toward the public sphere in the manner of later figures. His work has a reserved quality, technical and dignified, shaped more by sustained thought than by performance. Yet reserve should not be mistaken for weakness. Beneath the measured presentation lies a profound audacity. To remove Earth from the center was to unsettle a hierarchy that had structured learned imagination for centuries. To assign Earth multiple motions was to claim that the most obvious feature of experience, the stillness of the ground, was not trustworthy as a guide to cosmic order. There is a difference between speaking loudly and saying something large. Copernicus, when he finally published, did the second. The person who helped make that publication possible was Georg Joachim Rheticus, a young mathematician from Wittenberg who sought out Copernicus in the late 1530s. Their meeting changed the fate of heliocentrism. Rheticus recognized both the significance of the work and the danger that it might remain half-hidden in manuscript. He spent time with Copernicus, learned the system directly, and in 1540 published the Narratio Prima, the first printed account of the new astronomy. It was not yet the full treatise, but it served as an opening into the wider learned world. Rheticus's role in this history is easy to underestimate. Yet without him, the great book might have been delayed further, or perhaps never have entered circulation in the form it did. Scientific transformation often depends on such intermediaries, people who recognize that an idea needs not only insight, but passage. By 1543, De Revolutionibus finally appeared in print in Nuremberg. It was a dense and demanding work, addressed to mathematically trained readers rather than the general public. This matters, because the book did not announce itself as a manifesto of modernity. It entered the world as serious technical astronomy. Its arguments unfolded through geometry, tables, and model building, not through theatrical declarations about human destiny. Later memory has sometimes smoothed that complexity into a simpler symbolic event, as though the sun-centered universe arrived fully formed and immediately self-evident. In reality, the book asked a great deal of its readers. To see its power, one had to work through it. To accept its implications, one had to suspend a very old instinct for cosmic rest. And then there was the preface, printed at the front of the book, unsigned, was a short introductory note that told readers the mathematical hypotheses within need not be taken as literally true. They could be regarded as devices for calculation, useful for saving appearances without making strong claims about physical reality. The author of this preface was not Copernicus, but Andreas Osiander, a Lutheran theologian involved in the printing process. Whether he meant to protect the book, soften its implications, or simply express a common attitude toward astronomical models, the effect was profound. The preface gave cautious readers a way to engage the system without fully committing to it. It also complicated the historical image of Copernicus's intention, because the text that moved the Earth entered the world, partly framed as though it might not really mean what it seemed to say. That ambiguity, though frustrating in retrospect, may have helped the work survive its first encounters. A moving Earth was easier to contemplate if one could first treat it as a mathematical convenience. Yet the deeper strength of Copernicus's system was never merely computational. It offered a new order of comparison among the planets. Mercury and Venus belonged naturally near the Sun. The superior planets made better sense when Earth itself was moving. The sequence of the worlds acquired a fresh intelligibility. The cosmos began to resemble a structure organized from a central light, rather than a shell of motions arranged around a central weight. Even readers who remained unconvinced could feel the attraction of that order. The idea had a peculiar kind of pressure. It did not overwhelm experience, but it lingered in the mind because it made too many things look newly related. Still, the weaknesses were real, and they would matter for generations. Copernicus retained circular motions and epicycles because he was working within older commitments to uniform circular order. His system was simpler in some respects, but not simple in the way later myth would claim. More importantly, it lacked decisive empirical confirmation. No annual parallax had been observed. No new terrestrial physics had yet shown how a moving Earth could carry falling bodies and projectiles without producing the obvious disruptions people expected. In this sense, the title of this section holds its full weight. He moved the Earth without proving it. He altered the map before the road had been cleared. That gap between explanatory beauty and hard demonstration is one of the most fascinating psychological spaces in the history of science. Learned people were being asked to consider a theory that was, in many ways, more elegant than its rival, yet more difficult to believe as an account of reality. Beauty can persuade, but it can also mislead. Copernicus knew enough not to rely on beauty alone, and his caution reflects that awareness. He built arguments, comparisons, and calculations. He presented order as evidence of a deeper truth. Yet the old demands remained undefeated. Show us the Earth moving. Show us the stars shifting. Show us why stones still fall as they do. The system could reorganize appearances, but it had not yet compelled assent from nature itself. For some readers, that was precisely the point of fascination. A theory too crude to rival the old system would have been easy to dismiss. A theory that matched the heavens while also unsettling common sense was much harder to put aside. Copernicus had opened a new intellectual possibility that could not be easily forgotten, even by those who resisted it. Once one had seen the planets from within the sun-centered arrangement, the older cosmos no longer felt equally inevitable. The mind had acquired an alternative, and alternatives are dangerous things. They weaken necessity. They introduce the quiet thought that the world may not be as it first appeared, and that beneath the ordinary spectacle of sunrise and sunset, another order may be waiting. This did not mean that Europe suddenly became Copernican. Far from it. Many readers treated the model cautiously, selectively, or skeptically. Some admired its mathematical ingenuity while withholding belief. Others rejected it outright. Universities did not immediately reorganize themselves around the moving Earth. Daily life continued under the same sky, and the sky still looked the same. The importance of Copernicus lies elsewhere. He made the fixed Earth intellectually vulnerable. He gave later thinkers a structure within which new observations could matter differently. He created a world that had not yet been proven, but could now be tested, defended, attacked, refined, and imagined. And that is why the history does not pause with him. A rearranged cosmos, however beautiful, could not by itself break the old alliance between the senses and the heavens. To carry the argument forward, someone would need to look upward with a new instrument and find, in the visible fabric of the sky, signs that the inherited order was beginning to fail. And so, the next movement in the story did not begin with a decisive proof, but with a new way of seeing. In 1609, news began to circulate through Europe of a curious Dutch instrument that could make distant things appear near. It was, at first, an object of practical interest more than philosophical danger, useful for ships, watchtowers, and military advantage. Galileo Galilei, then a mathematics professor in Padua, did not invent the telescope, but he understood almost immediately what it could become. He learned enough about its principle to construct improved versions of his own, pushing its magnifying power well beyond the crude devices first reported. Then he did something that now feels obvious, but at the time was a quiet leap of imagination. He turned it upward. If you picture that moment from inside its intellectual atmosphere, the act carries a different weight. The heavens were not simply distant. They were elevated in a more fundamental sense. For centuries, the sky had been treated as a realm whose motions were pure, regular, and unlike the corruptible world below. To point a handmade optical tube toward the moon and planets was to invite the possibility that the old separation between heaven and earth might not survive inspection. Galileo did not yet know what he would find. But once the instrument was aimed at the sky, the cosmos inherited from Aristotle and Ptolemy entered a new condition. It had become vulnerable to close observation. The first great wound appeared on the face of the moon, to the naked eye. The moon had long seemed smooth enough to belong to the celestial order of perfection. Galileo saw something else. Along the line dividing light from shadow, bright points appeared detached from the illuminated region, then gradually joined it as the sunlight advanced. He interpreted these changing patterns the way a careful observer of landscapes might interpret dawn over uneven terrain. The lunar surface, he argued, was not a flawless sphere. It had mountains, depressions, roughness, relief. In other words, the moon resembled the Earth more than the old cosmology had allowed. That claim reached outward in ways larger than the moon itself. A rough lunar surface did not prove that Earth moved, but but it weakened the contrast on which so much of the older worldview depended. If a heavenly body could be scarred, shadowed, and topographically irregular, then the sky was no longer safely sealed off from the kind of physical reality known on Earth. One of the deepest habits of cosmic thought had begun to loosen. The heavens were still above, still remote, still majestic, but they were less untouchable than they had seemed. A realm long treated as qualitatively different was starting to look materially familiar. Galileo moved quickly. In early 1610, he published Sidereus Nuncius, the Starry Messenger, a slim book that announced several telescopic discoveries at once. It was one of the most effective acts of scientific publication in early modern Europe. The writing had urgency, confidence, and a sense of revelation sharpened by speed. Galileo understood something that would matter again and again in his career. Observation alone is not enough to change a world of thought. Seeing must be made public. It must be described, named, circulated, and attached to implications before others have time to absorb it calmly. In this respect, Galileo was very different from Copernicus. Where Copernicus had been patient almost to the point of concealment, Galileo was alert to the dramatic force of timely disclosure. Among the discoveries in the Starry Messenger, none struck the learned imagination more sharply than the objects he found near Jupiter. Night after night, he watched small points of light shift position around the planet, sometimes appearing on one side, sometimes the other, never wandering away like ordinary stars. He concluded, correctly, that they were bodies orbiting Jupiter. Today they are called the Galilean moons. Though Simon Marius, working independently, also observed them at nearly the same time. In Galileo's hands, however, they became something more than astronomical curiosities. Here was visible proof that not everything in the heavens revolved around the Earth. A second center of motion had appeared in the sky. That discovery did not establish heliocentrism, yet its psychological effect was immense. The old geocentric cosmos had not depended on the crude claim that literally every moving object circled the Earth in a simple way. Learned astronomers had long worked with more complex models than that. Still, the sight of Jupiter carrying its own miniature system did something profound to the imagination. It normalized plurality. It made the idea of local centers within a wider order feel concrete rather than merely abstract. If small worlds could circle a larger world other than Earth, then the cosmos had become more flexible than inherited common sense had suggested. Earth was no longer the obvious anchor of every celestial motion. It had rivals. Galileo also turned the telescope on the Milky Way and found that its pale, cloudy band dissolved into a multitude of faint stars. Nebulous patches that had seemed like soft luminous stains broke apart under magnification into crowded fields of points. Here again, the consequence was larger than the observation itself. The visible heavens were becoming denser, more particulate, more populous. The eye, unaided, had offered one kind of sky. The instrument disclosed another. Reality was beginning to separate from appearance in a way that could not easily be undone. The cosmos people thought they saw each night was no longer the cosmos the telescope disclosed. Soon there were the sunspots. These were not uniquely Galileo's discovery, and disputes over priority and interpretation followed, especially with Christoph Scheiner. But Galileo's involvement in the controversy mattered because the spots touched another nerve in the older worldview. Dark markings appeared on the sun, changed shape, drifted across its face. and returned in ways consistent with solar rotation. Here again, the heavens seemed mutable. The sun, long associated with purity and incorruptibility, was not an unblemished, changeless lamp. It was marked, dynamic, physically active. The celestial realm was shedding the old perfection point by point. What makes this sequence so powerful in historical memory is the cumulative texture of it. A rough moon, moons around Jupiter, countless stars hidden in the Milky Way, changing marks on the sun, and then, most famously, the phases of Venus. Each discovery struck a different part of the inherited cosmos. None on its own fully proved Earth moved. Together, however, they made the traditional picture increasingly unstable. The sky that had once seemed so well behaved was beginning to misbehave in too many ways at once. The phases of Venus deserve a slower look, because later retellings sometimes turn them into a simpler victory than they were. In the Ptolemaic arrangement, Venus remained on an epicycle, positioned in such a way that it could not display the full range of phases that a telescope revealed. Galileo observed that Venus, like the moon, waxed and waned through a complete sequence. Sometimes it appeared large and crescent-shaped, sometimes smaller and more fully illuminated. This made excellent sense if Venus orbited the Sun. As its position relative to Earth and the Sun changed, so would its apparent size and lit portion. The observation struck directly at the old Ptolemaic scheme. And yet there was an important limit. The full set of Venusian phases did not uniquely vindicate Copernicus. Tycho Brahe's geoheliocentric system, in which the planets orbited the Sun while the Sun and stars still revolved around a stationary Earth, could account for the same phenomenon. This is one of the most important subtleties in the entire history. Galileo's telescopic sky was devastating for some inherited structures, but it did not force a single conclusion as cleanly as later legend preferred. The evidence narrowed the field. It damaged the older geocentric machinery. It made the Copernican arrangement more plausible, more vivid, more attractive, but it did not yet trap nature into one unavoidable confession. There was still room, and in that room, resistance would continue to live. That tension between genuine breakthrough and incomplete closure is what gives Galileo his real historical shape. He was not the final prover of Earth's motion. He was the great destabilizer. He took a cosmos that had felt visually secure and turned it into something open, fractured, newly questionable. He gave observers reason to distrust the old certainty that the heavens were perfect and Earth uniquely different. He made ordinary readers, scholars, princes, and clerics confront a transformed sky through reports that were at once technical and startlingly readable. His genius lay partly in observation, partly in inference, and partly in rhetoric. Few scientists have ever been as quick to recognize the broader meaning of a discovery, and fewer still have moved so swiftly to attach that meaning to their own public identity. There was also a temperament inside all this that mattered greatly. Galileo's personality is difficult to separate from his science because he was so unusually skilled at making ideas enter public life. He wrote with irony, force, and clarity. He could be witty, cutting, and impatient with opponents he considered foolish or dishonest. He sought powerful patrons, understood the value of symbolic gestures, and named Jupiter's moons the Medicean stars to honor the Medici family. That was not a minor act of flattery on the margins of discovery. It was part of the larger ecology in which scientific claims gained protection, prestige, and audience. Galileo was a thinker of rare ability. but he was also a strategist of attention. This talent helped him and complicated him. It helped because the new astronomy needed advocates who could make the learned public feel its urgency. It complicated him because the force of his personality sometimes encouraged him to press beyond what the evidence securely allowed. He was right about many things. Magnificently right. But he was not right about everything. His later confidence that the tides offered a physical proof of Earth's motions, especially of its rotation and revolution, was mistaken. He disliked Johannes Kepler's willingness to accept lunar influence on the tides and instead developed his own mechanical account, which history did not vindicate. This detail is worth keeping in view because it preserves the human texture of the story. Galileo's brilliance did not exempt him from error. A scientist can see farther than contemporaries in some directions and still misread another crucial line of evidence. Even the telescope itself did not carry automatic authority. To modern ears, it may sound as though looking should have settled things. In practice, new instruments enter the world under conditions of trust that must be built. Some observers questioned what telescopes truly showed. Others struggled to interpret the strange appearances they produced. Optical artifacts, viewing conditions, instrument quality, and observer skill all mattered. A discovery made through magnification is not merely seen. It must be stabilized through repetition, shared practice, and argument. The early telescope opened the sky, but it also introduced new questions about mediation. People were no longer debating only what the heavens were like. They were also learning how to see through an instrument. And yet, despite these limits, something irreversible had happened. Once the moon had acquired mountains, once Jupiter had acquired satellites, once the sun had acquired blemishes, the old image of a simple, perfect heaven turning above a separate earth had become harder to keep whole. The change was not only intellectual, it was imaginative. If you had read Galileo, or looked through a good telescope yourself, the sky no longer rested above you with the same innocence. It had depth, texture, irregularity, concealed population. It had local systems and changing surfaces. It was not the polished shell inherited from tradition. It was a physical place. That alteration in feeling is one reason Galileo's role in the history of Earth's motion is so large. He did not supply the decisive proof critics demanded, but he changed the cost of disbelief. To remain with the old world after Galileo required more adjustment than before. One could still reject heliocentrism. Many intelligent people did. One could still hold to a stationary Earth while adopting a modified cosmic arrangement. But the debate had shifted. The burden was no longer carried by ancient authority alone. Fresh observation had entered the field, and with it came a new tempo of intellectual life. The heavens were no longer known only through inherited books and naked-eye tradition. They were becoming objects of investigative scrutiny. This change also widened the emotional horizon of astronomy itself. In the older cosmos, human beings stood at the center of a structured universe whose motions, though complicated, revolved in relation to a fixed world below. After Galileo's discoveries, the center felt less secure. Earth still felt motionless to the body. But visually and conceptually, it had begun to lose its privilege. Other bodies resembled it more than expected. Other worlds carried their own companions. The visible order of things no longer pointed so simply toward a single, unmoving stage. The human place in the cosmos was not yet transformed all at once, but the first strain of displacement had entered the bloodstream of European thought. It is important, though, not to smooth the story into inevitability. Galileo's discoveries inspired enthusiasm, doubt, reinterpretation, and resistance all at once. Some observers accepted the new sights while withholding heliocentrism. Others disputed parts of his reading, or favored the Tychonic alternative as a way to preserve a stationary Earth while accommodating the most troublesome observations. In other words, the old cosmos did not die because one man looked through a telescope and wrote beautifully about what he saw. It survived in altered form, defended by arguments that were often more careful and more scientifically serious than later myth would remember. That is why the sky in Galileo's time can be said to have begun to break, rather than to have broken cleanly. Cracks had opened in its inherited perfection. The old distinction between the celestial and the terrestrial had been badly damaged. The Ptolemaic arrangement had suffered a severe blow. Copernicus looked more alive than before. But the central mystery of this documentary remained unsolved. A moving Earth had become easier to imagine, easier to defend, harder to dismiss. It had not yet become unavoidable, and because it had not, the next stage of the story would belong to the resistance itself, to the learned objections, the alternative systems, and the uncomfortable fact that many of the people who still refused to let Earth move were not fools standing in the way of truth, but acute observers asking questions that had not yet been fully answered. And that resistance, when we slow down enough to hear it in its own voice, sounds very different from the caricature that later memory often preferred. It is easy to tell this chapter of the story as though the telescope had opened the heavens. Truth had arrived, and only stubbornness remained. But the 17th century did not feel like that from the inside. Galileo's observations had disturbed the old order. Certainly, they had made inherited cosmology less comfortable, less complete, less visually secure. Yet they had not dissolved the central objections to a moving Earth. For many learned observers, the question remained wide open. One system had been wounded, but the alternatives were still alive. And the most serious criticisms of heliocentrism came not from people refusing to think, but from people thinking very carefully indeed. Among them, no figure mattered more than Tycho Brahe. He had died in 1601, before Galileo's telescopic discoveries transformed the debate. But his influence only grew afterward because he had offered a model of the cosmos that seemed, to many, almost too clever to dismiss. In the Tychonic arrangement, the Earth remained fixed at the center. The sun revolved around the Earth, preserving terrestrial rest, while the other planets revolved around the sun. It was, in effect, a hybrid system, geometrically close in many practical ways to Copernicus, yet free of the most troubling demand of heliocentrism. Earth did not have to move. For observers trying to preserve common sense while also incorporating the increasingly persuasive mathematical order of the planets, Tycho's model offered shelter. There was a genuine brilliance in that compromise. It absorbed some of the explanatory elegance that had made Copernicus attractive, especially in accounting for the relative behavior of the planets, while refusing the physical and sensory burden of assigning motion to the Earth itself. One can almost feel why it appealed. If the sky already looked as though it moved around us, and if no clear terrestrial effect forced us to admit otherwise, why not let the planets circle the sun while the sun and stars still circled Earth? The arrangement may sound unstable to a modern ear, but within its own historical moment, it was a serious and often persuasive answer. It let astronomy change without requiring the whole structure of common experience to be overthrown. Tycho had another advantage, one that cut deeply into the Copernican case. He was among the most skilled naked-eye observers who ever lived. perhaps the greatest before the telescope. He measured stellar positions with extraordinary care, and in the process, he sharpened one of the oldest objections to Earth's annual motion. If Earth traveled around the sun, then the stars should exhibit parallax, their positions, viewed from opposite sides of Earth's yearly orbit, ought to shift slightly relative to one another. Yet Tycho could detect no such displacement. This absence was not vague or casual. It emerged from disciplined observation. To preserve heliocentrism, one had to say that the stars were vastly farther away than earlier astronomers had imagined, so far that even Earth's enormous orbital path was too small a baseline to reveal the shift. That answer solved one difficulty by opening another. If the stars were that remote, then their apparent sizes became a serious embarrassment. Tycho and others observed that stars were not dimensionless mathematical points to the eye. They appeared as tiny disks. If those visible disks belonged to stars at incomprehensible distances, then the stars themselves had to be absurdly large, in some cases rivaling or surpassing the entire orbit of the Earth. For anti-Copernicans, this seemed preposterous, a theory that demanded a universe so immense and stars so physically enormous could be taken as a sign that something had gone wrong in the reasoning. Today we know that those apparent stellar disks were not true physical sizes, but optical effects shaped by the limitations of vision and later by diffraction in telescopes. But that was not available knowledge then. The objection was built from sincere observation, interpreted through the best optics the age possessed. There is a deep fairness required here if we want to understand the past honestly. The missing parallax argument was strong because the missing parallax was real, at least at the level of available instruments. The star size objection was strong because the apparent disks also seemed real. Critics of Earth's motion were not inventing obstacles from bad faith. They were looking, measuring, and asking what the evidence permitted. The future would eventually answer them, but it had not answered them yet. One of the reasons heliocentrism took so long to secure is that some of the best objections were produced by exactly the kind of disciplined empirical reasoning that science later came to prize. The sky was not the only place where trouble remained. Down on Earth, ordinary motion still refused to cooperate with the Copernican imagination. If the planet rotated, what should happen to objects dropped from a height? A tower, after all, would be carried eastward by Earth's daily turning. A stone released from the top might be expected to lag behind and land west of the base. If the ground itself rushed beneath the air, then the behavior of clouds, birds, smoke, arrows, and cannonballs ought to show some disturbance. Even if one granted that the atmosphere somehow shared the motion, questions remained. Why did projectiles not display obvious asymmetries in different directions? Why did bodies fall straight down, or seem to? Why did the mechanics of daily life keep agreeing with stillness? These were not idle puzzles. They marked the edge of a physics that had not yet been remade. In an Aristotelian framework, motion required causes of a certain kind, and rest at the center of the cosmos had a deep natural logic. To say the Earth moved meant more than changing an astronomical diagram. It meant disturbing the inherited understanding of how bodies behaved. Without inertia, without a mature concept of relative motion, without the later mechanics that would make shared motion intelligible, the rotating Earth seemed physically confused. One can see this clearly in debates over falling bodies and projectiles. Anti-Copernicans did not merely say that motion felt wrong. They asked how a moving Earth could fail to reveal itself in the ordinary dynamics of terrestrial life. That question had force because the new astronomy was outrunning the old physics without yet replacing it. Galileo, as we have seen, tried to answer some of these concerns, and he made important steps toward a new understanding of motion. Yet in the 17th century, the matter did not feel settled. The everyday world still seemed to stand on the side of the fixed Earth. If a sailor drops something from the mast of a moving ship, and it lands near the foot of the mast, modern physics can explain why shared motion produces that result. But the general framework that makes such reasoning feel natural took time to develop. Before that framework became stable, analogies and counterexamples could be disputed, and critics had room to insist that terrestrial experience remained a stubborn ally of geocentrism or geoheliocentrism. There was also the issue of scale, which affected the imagination almost as much as the mathematics. A moving Earth requires a cosmos that can tolerate vast emptiness. The stars must be removed to astonishing distances, not because anyone desired grandeur for its own sake, but because otherwise the missing parallax could not be explained. For some thinkers, this expansion of the universe was philosophically or theologically acceptable, even beautiful. For others, it felt extravagant. The older cosmos, though complex, was proportioned in a way that seemed intelligible to the human mind. The Copernican universe appeared to waste space on a scale difficult to justify. This was never the only argument against Earth's motion, but it reinforced the sense that heliocentrism came at a high conceptual price. If we listen to the anti-Copernican case in its strongest form, a pattern emerges. Critics could say that heliocentrism asked them to surrender too much too soon. It asked them to distrust the senses, reinterpret the heavens, accept a physics they did not yet possess, and imagine stars at distances that dissolved the old proportions of the world. All this was requested before the theory had delivered the decisive observational signature everyone knew to look for. That is why mere elegance could not settle the matter. Copernicus had reorganized the sky in a compelling way, and Galileo had made the old heavens look newly fragile. But opponents could still point toward missing evidence and say, with considerable justice, that plausibility was not proof. One of the most revealing figures here is Giovanni Battista Riccioli, the 17th century Jesuit astronomer whose massive Almagestum Novum, or New Almagest, published in 1651, surveyed the arguments with remarkable breadth. Riccioli is often remembered too simply as a defender of the old Earth, but his role is more interesting than that. He cataloged dozens upon dozens of arguments for and against the Earth's motion, and when modern historians revisit his work, they are often struck by how little of it reduces to mere scriptural repetition. Only a small fraction of his objections were explicitly theological. Most were observational, physical, or philosophical. Riccioli took telescopic astronomy seriously. He accepted some of the new discoveries, yet he remained unconvinced that Earth's motion had been demonstrated. His discussions of falling bodies and stellar appearance are especially important because they show how mature the anti-Copernican position could be. Riccioli and others considered whether rotating Earth should create detectable deflections in objects dropped from heights or fired from artillery. They reflected on how a moving observer ought to register the world, and where such effects should appear if the new system were true. Some of these arguments rested on mistaken premises. Some anticipated, in a rough way, issues that later physics would clarify, yet taken together, they formed a body of resistance that cannot be dismissed as anti-scientific. It was science in an earlier stage of self-revision, pressing hard against a new idea and demanding a better account of nature before yielding. There was, too, a more personal and institutional side to this refusal. Learned people had been trained for generations inside a cosmos whose conceptual stability touched many branches of knowledge. Astronomy was connected to natural philosophy, calendar reform, theology, pedagogy, and the prestige of classical authorities. To abandon the fixed Earth was not merely to prefer one technical model over another. It was to loosen the interlocking confidence of an educational world. That did not make resistance irrational. It made it costly. Ideas do not live alone in the mind. They live among institutions, habits of interpretation, disciplinary boundaries, and reputations. A new cosmos had to fight its way through all of that, while still lacking the one clean proof everyone hoped for. This is one reason the Galileo affair, though historically important, can distort the wider picture if it is made to carry too much symbolic weight. Conflict with church authority did matter. Scripture could certainly be invoked, and theological concerns were real. But if we allow that dimension to overshadow everything else, we lose the intellectual dignity of the scientific objections themselves. Many opponents of Earth's motion were not simply defending doctrine against evidence. They were defending a view of nature that still seemed better supported on several crucial points. A mature documentary needs to preserve that complexity. The Earth did not fail to move because authorities forbade it. Rather, the evidence available at the time remained incomplete enough that even very capable observers could remain unconvinced without intellectual dishonesty. And there is something almost beautiful in that resistance. If beauty can be found in rigor, science advances partly because new ideas are proposed, but also because they are interrogated from every side. A theory too weak to survive hard questioning does not deserve victory. The long delay in proving Earth moves was painful for the Copernican case, yet it also forced later thinkers to do deeper work. They would have to explain motion itself differently. They would have to refine observational techniques. They would have to reconcile celestial order with terrestrial mechanics. In that sense, the anti-Copernican challenge was not merely an obstacle. It was a pressure that made the eventual transformation more solid. Still, for those drawn toward heliocentrism, the 17th century could feel like living in a suspended state. The old world had been badly compromised, and yet it would not fall. The telescope had changed the look of the heavens, and yet the Earth still felt unmoved. The planets made better sense around the sun, and yet the stars refused to shift. The idea at the heart of the new astronomy was compelling enough to survive, but not strong enough to finish the argument. That prolonged tension is easy to underestimate because hindsight compresses it. In lived time, decades passed inside this unresolved condition. People thought, observed, argued, published, recalculated, and still the central issue remained strangely open. You can almost feel the peculiar mental atmosphere of that period. Imagine looking through a telescope and seeing enough to disturb your inherited universe, but not enough to settle the matter completely. Imagine working through geometric models that suddenly seem cleaner and more expressive than the old ones, while your colleagues point to the missing parallax and ask, reasonably, where the proof is. Imagine realizing that the body says one thing, the telescope another, the mathematics a third, and the physics is still being rebuilt. This was not the triumph of truth over blindness. It was an age in which several ways of reading nature overlapped, collided, and refused easy reconciliation. What finally made the difference? Then, would have to be more than another round of polemic. It would require a universe in which Earth's motion could be understood not as a clever rearrangement or a troubling possibility, but as part of a deeper and more coherent account of how bodies move at all. The objections had revealed the scale of the task. To answer them fully, astronomy would need help from a new physics, and that new physics would begin to take shape in the minds of those who were willing to imagine motion in a less intuitive, more profound way than the old stillness had ever allowed. And so the question could no longer remain only in the sky. The resistance to Earth's motion had exposed something important, a new arrangement of the heavens. However elegant, was not enough. Telescopes could trouble inherited certainties, and mathematical models could reveal hidden order. But as long as motion itself remained conceptually unstable, the fixed Earth would keep some of its old authority. To many observers, heliocentrism still felt like an astronomer's rearrangement rather than a fully believable world. If the Earth truly traveled and turned, then the universe needed to become a place in which such motion made physical sense. That change would come slowly, and it would pass through two minds very different in temperament, style, and historical position, yet strangely linked by the same deeper task. They did not deliver the final observational proof. What they did was in some ways just as necessary. They taught the cosmos how to move. Johannes Kepler came first, and there is something almost fitting in the restlessness of his life. He was born in 1571 in the Holy Roman Empire, into a world torn by religious conflict, intellectual transition, and political uncertainty. His circumstances were often unstable. He taught, calculated horoscopes, moved from city to city under pressure, defended his mother against a witchcraft accusation, and spent years working in the shadow of larger patrons and harsher events. Yet within that unsettled life, there was a remarkable steadiness of purpose. Kepler wanted more than a calculating scheme. He wanted a universe whose geometry, causes, and harmonies belong together. In this, he stands apart from any simple picture of astronomy as mere curve fitting. For him, the heavens were intelligible because they were ordered, and ordered because they were, in some deep sense, meaningful. Kepler had embraced Copernicus early, but he did so in a way that already pointed beyond Copernicus himself. The sun-centered arrangement, to his mind, was not attractive only because it simplified planetary behavior. It also made the sun physically and symbolically central. Light, motive power, intelligibility, divine geometry. These things gathered around it in his imagination. Kepler's thought could be mystical in tone, but it would be a mistake to hear that as softness. He was rigorous, inventive, and often painfully honest with data. His speculative hunger and his mathematical discipline lived side by side. That combination is one reason he matters so much in this story. He was willing to search for cosmic beauty, yet he was also willing to surrender cherished forms when observation demanded it. The most famous example began with Mars. Kepler inherited from Tycho Brahe an extraordinary body of planetary observations, far more precise than anything earlier astronomers had possessed. That inheritance was decisive. Tycho himself had not accepted Earth's motion, but the accuracy of his records gave later astronomy a sharper blade. Kepler set out to understand the orbit of Mars within a Copernican framework. What he encountered there was not a neat confirmation of inherited ideals, but a stubborn mismatch. Again and again, circular paths and traditional adjustments failed to align with the data closely enough. the discrepancies were small, but to Kepler they mattered. He was not willing to dismiss a few minutes of arc as negligible decoration. The heavens, if they were lawful, should fit. That insistence carried him into one of the great acts of intellectual renunciation in scientific history. For centuries, circles had been favored in astronomy for reasons that were mathematical, philosophical, and aesthetic all at once. Circular motion seemed perfect, fitting for heavenly bodies and worthy of a cosmos believed to reflect a higher order. Copernicus himself, despite moving Earth and reordering the planets, had retained the preference for circles. Kepler let it go. Mars did not move in a perfect circle. It moved in an ellipse, with the sun at one focus. This was not merely a technical correction. It was a wound to an ancient taste. A shape long associated with imperfection had entered the architecture of the heavens. To modern readers, an ellipse can feel almost modest, a small geometric adjustment. In Kepler's time, it was more unsettling than that. It meant that the celestial order could be lawful without conforming to inherited ideals of symmetry. Reality was not required to preserve human preferences for perfect forms. The sky could obey strict mathematical relations while abandoning the shapes that philosophers had once considered worthy of it. This was a decisive step in making Earth's motion believable, because it replaced part of the old cosmos with something less ornamental and more dynamic. Planets were no longer carried along by constructions designed to preserve ideal circles. They moved in paths that could be traced to actual regularities in nature. Kepler did not stop with the ellipse. From his work emerged what later generations would call his first and second laws of planetary motion. A planet travels in an ellipse with the sun at one focus, and it sweeps out equal areas in equal times. The second claim is especially important for the feel of the universe it introduces. A planet does not move with rigid uniformity. It speeds up when nearer the sun and slows when farther away. Once again, the heavens had become more physical and less ceremonial. Motion was not a perfect, abstract turning performed in obedience to ancient geometric dignity. It had variation, pace, relation. The planet behaved as though the sun mattered causally. That causal ambition was one of Kepler's great contributions. He did not want astronomy to stop at describing where planets would appear. He wanted to know why they moved as they did. He imagined, in ways that were still incomplete and often speculative, that the sun exerted something like a motive influence outward through space. His language did not yet possess gravitation in the Newtonian sense, but his instinct was moving in that direction. The cosmos was beginning to acquire forces. It was no longer enough to save appearances. One had to ask what in nature generated the pattern. In that shift, Earth's motion became easier to inhabit. A moving planet no longer needed to be treated as a sheer anomaly. It could be one member of a lawful solar family, linked to a source of motion at the center. Kepler's third law, published later in Harmonique Mundi in 1619, deepened that family resemblance. The squares of the planet's orbital periods were proportional to the cubes of their mean distances from the sun. However one states it mathematically, the emotional force of the discovery lies in relation. The planets were not simply circling the sun in isolation. Their distances and times belonged to a single numerical order. What one world did was bound, quietly and exactly, to what another did. The solar system had become a structured whole. For heliocentrism, this mattered enormously. Earth was no longer just the world we happened to stand on, reluctantly moved from the center by astronomers. It had become one planet among others, sharing a common set of laws This did not settle the matter for everyone. Kepler's laws described planetary motion with extraordinary power, but they did not yet provide the full physical account that critics had demanded. He had made the system vastly more coherent, more predictive, more real in its internal architecture. Still, the deeper mechanics of moving bodies remained unfinished. Why should an orbit take this form? What exactly linked falling objects on Earth with circling bodies in the sky? How could one and the same universe hold both the apple and the moon within a common logic? Kepler had pushed the question forward with astonishing courage. Yet there was more to be done. The Earth had become easier to imagine in motion, but the total framework of motion had not fully arrived. Then came Isaac Newton. Newton's life has often been retold in ways that blur the strangeness of his mind into the smooth silhouette of genius. Yet if we slow down, the texture matters. He was born in 1642, the year Galileo died, and from an early age displayed an inwardness almost as notable as his brilliance. He could be secretive, intensely competitive, solitary, suspicious, and capable of concentration so prolonged that it seems almost severe. He worked across mathematics, optics, mechanics, alchemy, theology, and chronology with an appetite that did not respect later disciplinary boundaries. The famous years in the mid-1660s, when plague closed Cambridge and he spent time away from the university, have sometimes been romanticized into a burst of isolated revelation. There is truth in the extraordinary fecundity of that period, but it was followed by decades of refinement, dispute, and conceptual hardening. Newton's achievement was not a bright instant. It was a vast act of consolidation. When the Philosophiae Naturalis Principia Mathematica appeared in 1687, it changed the terms of the conversation. Newton did not merely add another astronomical model to the field. He supplied a new mechanics. His laws of motion and the law of universal gravitation tied together phenomena that earlier systems had kept apart. Bodies persist in their state of motion unless acted upon. Acceleration depends on force. Every mass attracts every other mass according to a precise relation involving their masses and the distance between them. These ideas can seem abstract when stripped to formulae, but their historical impact was deeply concrete. They erased the old divide between terrestrial and celestial physics. The same principles that described a falling object on Earth could describe the path of the moon. The heavens and the ground beneath one's feet had entered a common order. That unification is difficult to overstate. In the older cosmos, upward and downward, heavenly and earthly, circular and rectilinear, had belonged to different layers of being. Newton collapsed those differences into a single, intelligible framework. An orbit was no longer a mysterious kind of motion reserved for elevated bodies. It was what happened when inertia and attraction worked together. A planet moved forward, continually falling toward the sun, yet never reaching it because its own motion carried it onward. The moon fell toward Earth in the same broad sense that an apple did, though with a sideways motion sufficient to keep missing the ground. Suddenly, the moving Earth was no longer a conceptual orphan. It was a lawful result of universal mechanics. There is a quiet beauty in how this changed the emotional temperature of the debate. Before Newton, critics could still feel that heliocentrism asked them to accept a kinematic picture without a persuasive physical basis. After Newton, Earth's motion belonged inside a majestic and coherent account of nature. The planets no longer needed invisible crystalline spheres or special celestial principles unrelated to terrestrial events. Their paths arose from causes that operated everywhere. A person standing on Earth and a body circling in space now lived under the same laws. Motion had become less intuitive in one sense, because Newtonian mechanics often ran against unexamined bodily assumptions, but more believable in a deeper one. The universe had acquired a grammar capable of carrying the sun-centered system with intellectual dignity. Newton also returned, in transformed form, to Kepler's achievements. The laws Kepler had found empirically could now be derived, approximately and with great power, from deeper principles. Elliptical orbits were not fortunate patterns discovered in data alone. They emerged from the relation between inertia and inverse square attraction. Kepler's world of harmonies and numerical order had been absorbed into a larger mechanics. One can almost feel the relief this offered to the scientific imagination. A theory that had once seemed daring because it rearranged appearances now appeared profound because it expressed the structure of nature. Earth's motion was no longer only a useful way to read the sky. It had become part of how the universe actually worked. And yet, for all that Newton accomplished, an interesting tension remained. His system made heliocentrism physically compelling, even overwhelmingly so for many thinkers. But the direct observational signatures long demanded by critics were still not all in hand. Annual stellar parallax had not yet been detected. One could explain beautifully why Earth ought to move, why planets should orbit, why the moon remains in its path, and why the same forces govern the falling of bodies and the turning of worlds. But if someone insisted on asking where precisely, the heavens themselves revealed Earth's yearly displacement, the answer remained elusive. The theory was now magnificent. Nature still withheld one of its cleanest little geometrical confessions. This delay is one of the most subtle and revealing features of the whole story. Scientific conviction does not always wait for every direct sign to appear. Sometimes a web of explanation becomes so powerful, so mutually reinforcing, that a theory wins broad allegiance before all the hoped-for observations arrive. That is part of what happened in the Newtonian age. The moving Earth had become the natural inhabitant of the new mechanics. It fit a universe governed by universal gravitation far better than the old stillness fitted. Even so, the historical memory of the earlier objections did not simply evaporate. They lingered as unfinished business, reminders that one can possess an extraordinarily persuasive framework and still hunger for one more clear piece of evidence. There were also terrestrial hints that Newtonian physics could make sense of old questions in fresh ways. The Earth, if rotating, should not be a perfect sphere. Centrifugal effects would slightly swell it at the equator and flatten it at the poles. This became a matter of geodesy, measurement, and controversy in the 18th century, and the eventual confirmation of Earth's oblateness gave further support to the rotating planet envisioned by Newtonian theory. Here again, the pattern is instructive. The universe was becoming friendlier to motion through a series of convergences. Mathematical law, astronomical prediction, and the shape of the Earth itself were beginning to speak in related accents. The moving Earth was not yet demonstrated in every desired way, but the world increasingly behaved as though Newton and his predecessors had found something true. It is also worth lingering for a moment on the psychological contrast between Kepler and Newton, because it tells us something about the development of ideas. Kepler pushed toward order with a mix of longing, intuition, mathematical fidelity, and metaphysical imagination. He wanted the solar system to make sense as a living harmony. Newton, by contrast, built an architecture of law so austere and powerful that it could hold the motions of worlds without rhetorical ornament. One mind sought the shape of divine geometry in the heavens. The other wrote principles capable of turning celestial motion into calculable necessity. The difference matters, but so does the continuity. Both helped move Earth from the edge of plausibility toward the center of physical reason. By the turn of the 18th century, then, the old debate had changed in character. The fixed Earth no longer seemed like the default home of common sense, challenged only by speculative astronomers. It had become a position increasingly out of step with the deepest structure of the new physics. Yet the story's central tension had not vanished. The final satisfaction still lay ahead. One could now inhabit a moving Earth intellectually. One could see why it belonged within the order of the cosmos. One could even begin to treat old objections as relics of an outdated mechanics. But the long historical desire for a direct observational signature remained strangely alive. And that is what gives the next chapter its peculiar beauty. After centuries of argument, after the slow construction of a universe in which Earth's motion finally made profound physical sense, the decisive evidence would not arrive exactly where everyone had expected, or in quite the form they had been waiting for. And when that next answer began to form, it did so in a way that would have felt almost mischievous to anyone who had lived through the long argument. For generations, the missing sign had been clear in principle. If the Earth traveled around the sun, the stars ought to betray that motion through parallax, a slight annual change in their apparent positions caused by the observer viewing them from different points in Earth's orbit. This was the geometrical signature people had been waiting for, the elegant little shift that would answer one of the oldest objections to heliocentrism. By the early 18th century, the intellectual world had changed dramatically. Newtonian physics had made Earth's motion deeply plausible. The universe had, in a sense, learned how to carry a moving planet. But the sky had still not yielded the long-promised displacement. The theory was powerful, even majestic. The stars remained stubbornly still. That is what makes the scene in the 1720s so quietly beautiful. The search had narrowed from the scale of whole systems to the discipline of minute measurement. Grand cosmological arguments were no longer enough. If the heavens were going to confess Earth's motion more directly, it would happen through painstaking attention to a very small effect, one so slight that earlier centuries had simply lacked the precision to isolate it. This is one of the great changes in the history of science. Truth no longer arrives as an overwhelming spectacle. It approaches as a deviation, a fraction, a tiny stubborn difference between what is expected and what is actually seen. James Bradley was well suited to such work. He was mathematically gifted, observationally patient, and temperamentally inclined toward care rather than flourish. He had studied at Oxford, been influenced by John Flamsteed and Edmund Halley, and belonged to a generation of astronomers working in a world transformed by Newton, but still burdened with unresolved observational questions. Bradley does not carry the same legendary aura as Galileo or Newton, and that is part of why his role in this story is so appealing. He was not a great public combatant, not a self-dramatizing figure moving through controversy with literary force. He was the kind of mind that keeps looking when the data do not quite behave. And that kind of mind can change history just as surely. Alongside him stood Samuel Molyneux, an amateur astronomer of means and political standing, whose house at Kew became the site of one of the most delicate observational efforts of the century. The practical setup mattered. They needed a star that passed close to the zenith in southern England, because a star high overhead minimized certain observational difficulties, especially atmospheric refraction. They fixed on Gamma Draconis, a star in the constellation Draco, well placed for the purpose. In 1725, Molyneux had a carefully constructed zenith sector installed in his house, a specialized instrument designed to measure tiny changes in the star's position as it crossed near the vertical. The aim was straightforward in concept. They would watch the star over time and see whether the Earth's annual motion revealed itself in the long-awaited shift. There is something wonderfully restrained about the whole enterprise. No spectacle, no cheering audience, no dramatic apparatus dominating a public hall, just a room arranged for precision, an instrument fixed with care, a star chosen for its observational usefulness, and a question old enough to have passed through centuries of doubt. One can imagine the rhythm of that work. The repeated observations, the comparisons, the quiet hope that nature might at last produce the missing piece. After so much debate, so much philosophical reconstruction, so much mathematical and physical labor, the answer might come down to a tiny movement in a single star. At first, it seemed as though something was indeed happening. But almost immediately, the behavior of Gamma Draconis began to trouble the observers. The star's apparent position shifted over the course of the year, yet not in the way parallax alone should have produced. The pattern was real enough to demand attention, but it resisted the expected interpretation. If one has followed this documentary from the beginning, the significance of that moment begins to shimmer. The observers were finally seeing an annual effect in the stars. The very class of phenomenon critics of Earth's motion had long demanded, and yet the sky was answering in the wrong language. That was the crucial difficulty. A lesser observer might have forced the data into the hoped-for pattern, declared success too early, or blamed the instrument and moved on. Bradley did neither. He continued observing. And when Molyneux's work was interrupted, Bradley carried the investigation forward with characteristic persistence. The star's displacement was systematic, not accidental. It repeated with the year, but its phase and character did not match the simple parallax explanation people had expected. The heavens were not merely withholding the old answer, they were offering a different one. To appreciate how subtle this was, it helps to step for a moment into the logic of the observation itself. Parallax depends on a change in the observer's position, as the Earth moves from one side of its orbit to the other. A nearby star should appear to shift slightly against the more distant background. The effect is geometric. But what Bradley eventually realized was that another annual effect could arise from something altogether different: the combination of Earth's orbital motion with the finite speed of light. Light does not reach the observer instantaneously. If the observer is moving while the light arrives, then the telescope must be tilted slightly in the direction of motion to catch the starlight properly. The result is a small apparent displacement in the star's position. A later analogy would make the idea famous. If rain falls vertically on a windless day and you stand still, it enters a tube held straight up. But if you begin walking, you must tilt the tube forward to catch the rain, even though the rain itself is still falling vertically. In a similar way, if starlight arrives while the Earth is moving through space, the observer's motion alters the apparent direction from which the light seems to come. The star has not actually shifted in space because of parallax in the expected sense, and rather, its apparent place is displaced because the Earth is moving while the light takes time to enter the instrument. This became known as the aberration of starlight. What makes Bradley's discovery so historically perfect is that it depended on a previous revolution in thought. Without the recognition that light has a finite speed, the explanation would have been hard even to imagine. That recognition had been powerfully advanced a few decades earlier by old Roemer's work on the eclipses of Jupiter's moons. Roemer had inferred that light takes time to travel. Using variations in the observed timings of those eclipses as the Earth moved in its orbit. Bradley's result belongs to the next stage of that story, the finite speed of light, once a subtle and astonishing idea in itself, now combined with Earth's motion to produce a visible astronomical effect. The proof was emerging from the interaction of two once unsettling truths. Bradley announced his findings in 1728, and the intellectual importance of the result was considerable. Aberration was not the parallax astronomers had set out to find, but it was direct evidence of Earth's orbital motion. The effect depended on Earth moving through space while light traveled at a finite speed. If the Earth were stationary, the annual pattern Bradley measured would not arise in that way. Here, at last, was a phenomenon in the stars that did not merely fit comfortably inside a heliocentric world view or derive from a majestic theory of gravitation. It was an observed effect tied directly to Earth's motion around the sun. The irony is part of the charm. A proof that had eluded the very form everyone anticipated arrived wearing different clothes. Still, as so often in this story, reality refused to simplify itself completely. Bradley's work did not instantly erase every lingering complexity, nor did it end the history of proof. Aberration is subtle. It is direct evidence, but not the same clean geometric signature that centuries of anti-Copernican debate had fixed upon. One can feel why the discovery was both decisive and strangely incomplete at the same time. It answered the larger question in a powerful way. Yet the old longing for parallax, the pure shift produced by changing vantage point, remained alive. The stars had moved at last, but they had moved for a reason different from the one most people had been waiting to see. Bradley's own work, characteristically, did not stop at the first explanation. Continued observations revealed additional irregularities. And in time, he identified another phenomenon now known as the nutation of Earth's axis. A subtle wobble produced chiefly by lunar influence on the planet's rotational axis. That later discovery is not the central point here, but it tells us something important about the manner of the man and about the scientific process itself. Nature often answers one question by exposing another. A data set once thought to contain a single desired effect turns out to carry several overlapping truths, each requiring patient separation. The more exact the science becomes, the less the universe behaves like a clean diagram, and the more it resembles a layered conversation. There is a psychological elegance in Bradley's role that is worth lingering over. Earlier figures in this documentary often transform the debate by bold conceptual shifts, public controversy, or sweeping theoretical synthesis. Bradley's contribution feels quieter, but perhaps for that reason it reveals something especially pure about scientific discovery. He did not win this chapter by dazzling the world with rhetoric. He won it by refusing to discard an anomaly. He trusted the stubbornness of the measurement enough to let it teach him something he had not gone out to learn. That is a rare discipline. Most people, in science as in life, seek confirmation of what they already suspect. Bradley found a truth because he took the risk of remaining with what did not fit. And there is another kind of beauty here. 2. For centuries, critics of Earth's motion had insisted that if the planet traveled through space, the star should testify somehow. The old objection had teeth because it was built on a real intuition. A moving observer ought to detect the consequences of motion. Bradley's discovery vindicated that instinct while transforming its expression. Yes, the stars did testify. They did so not first through the simple triangulation everyone had imagined, but through the finite travel time of light itself. The heavens had not been silent after all. They had only been speaking a language that earlier, astronomy was not yet equipped to hear. This is one of the moments in the history of science when the path to truth feels almost more revealing than the truth itself. People often imagine discovery as a sequence of successful intentions. A scientist asks the right question, performs the right experiment, and obtains the right answer. But the real history is often more oblique. One searches for one thing and encounters another. Instruments are built to detect a long-expected effect, and instead they uncover a phenomenon no one had placed at the center of the story. Knowledge advances not because human beings always know what to seek, but because sometimes they are disciplined enough to recognize significance when it arrives from an angle. By the standards of the 18th century, Bradley's result was a major triumph for the moving Earth. It gave heliocentrism something more than elegance, more than physical coherence, more than telescopic plausibility. It gave it an annual stellar effect tied directly to Earth's orbital motion. The long resistance of the fixed Earth had lost one of its strongest protections. Yet the old historical rhythm had not vanished altogether. Some forms of satisfaction still remained deferred. The direct geometrical shift of a star due to changing perspective across Earth's orbit. The pure stellar parallax that had haunted the debate since Copernicus and before was still too small to be pinned down with confidence. And so a curious emotional atmosphere settled over astronomy. A profound answer had been found, but it had not exhausted the desire for completion. The universe had yielded evidence no one was explicitly looking for, and that evidence was enough to transform the debate. Still, the older challenge had left its mark so deeply that astronomers continued to pursue the elusive parallax itself. They wanted not only a motion-sensitive sky, but the original observational signature in its clearest form. The Earth, by now, had been made mobile in theory, in mechanics, and through aberration in observation. Yet the stars still held back one last kind of agreement that would matter enormously in the next century. Because once the instruments improved enough, and once observational discipline became fine enough, the very effect that had failed to appear for generations would finally emerge. Faint, difficult, and long overdue from the stellar background where it had been waiting all along. And when that older, more geometrical sign finally came, it did not arrive with the force of revelation so much as with the delicacy of something almost too small to trust. For centuries, stellar parallax had been the missing testimony. It was the effect everyone understood in principle, the one critics of Earth's motion had invoked again and again. If our planet traveled around the sun, then the stars, at least the nearer ones, ought to seem to alter their positions very slightly over the course of a year, as the observer was carried from one side of Earth's orbit to the other. The idea was simple enough to sketch on paper. What defeated generation after generation was scale. The stars were so remote that their shifts were minute beyond anything earlier astronomy could securely grasp. By the 19th century, the intellectual case for Earth's motion was already immense. Newtonian physics had made it physically coherent. Bradley's discovery of aberration had given direct observational evidence of orbital motion. Yet the old desire remained. Astronomers still wanted the classical answer. the direct triangulation of a star against the background, the small annual displacement that would finally complete a very long argument. What made that desire so persistent was not only its scientific value, but its symbolic charge. Parallax had once been the strongest observational objection to a moving Earth. Anti-Copernicans had asked, with real force, why the stars did not shift if the Earth truly moved. Copernicans had replied that the stars must be unimaginably far away. To measure parallax, then, would do more than add another astronomical constant to the growing body of science. It would vindicate one of the oldest and boldest claims of the heliocentric worldview. It would show that the apparent silence of the heavens had never been a refutation, only a sign of how vast the universe really was. By the early decades of the 19th century, the technical situation had begun to change. Instruments were better. Observational methods were more disciplined. Astronomy had become more institutional, more professionalized, more heavily shaped by precision. This was an age in which small differences mattered profoundly. The challenge was no longer to imagine how parallax might exist, nor to defend its plausibility within a theoretical system. It was to isolate an effect so tiny that it could be confounded by instrumental error, atmospheric conditions, observational bias, and the subtle motions of the stars themselves. Here, more than ever, astronomy became an art of disciplined suspicion. To claim success too early would be disastrous. To hesitate too long might mean losing priority to a rival observer working under another sky. One of the men who entered this field most forcefully was Friedrich Wilhelm Bessel. His background already carried some of the strange energy that often accompanies great precision. He had not followed the clean, classical path of elite academic formation from the beginning. He worked in a commercial office as a young man, educated himself intensively, and rose through talent, discipline, and extraordinary computational skill. By the time he became director of the observatory at Königsberg, he had established himself as one of the finest astronomers in Europe. Bessel's temperament suited the problem of parallax. He was rigorous, technically formidable, and deeply attentive to measurement. The universe, for a mind like his, was something one approached through repeated correction, through patient comparison, through the refusal to let desire outrun evidence. Choosing the right target mattered enormously. A star with a detectable parallax needed to be close enough, in relative terms, for the effect to stand some chance of measurement. Yet closeness, in the astronomical sense, could not be known directly in advance. Astronomers had to infer it from hints. One useful clue was proper motion. The slow drift of a star across the sky over long periods of time. A large proper motion could suggest that a star was relatively near, though it was no guarantee. Bessel selected 61 Cygni, a rather unassuming double star in the constellation Cygnus. It did not blaze like Sirius or Vega. Its attraction was subtler. It appeared to move noticeably against the background over time, which made it a promising candidate for nearness. The instrument Bessel used was a heliometer, a device especially suited to measuring tiny angular separations. A heliometer had originally been designed for measuring the apparent diameter of the sun, but in practiced hands, it became an instrument of exquisite comparative astronomy. Bessel could measure the position of 61 Cygni relative to neighboring stars and watch for the annual changes that would betray parallax. Even this description makes the work sound more straightforward than it felt in practice. Every observation had to pass through the fragility of instruments, the instability of the air, and the risk that the comparison stars themselves might not be as fixed as hoped. Precision astronomy is often romanticized as the science of exactitude. In lived reality, it is also the science of all the small ways exactitude can fail. While Bessel pursued 61 Cygni from Königsberg, others were circling the same prize. Wilhelm Struve, a major figure at the Dorpat Observatory and later at Pulkovo, worked on parallax as well, especially for Vega. Thomas Henderson, operating from the Cape of Good Hope, had made observations suggesting a measurable parallax for Alpha Centauri, the bright southern star system that is in fact one of the nearest to Earth. The race was not necessarily conducted as open personal drama, but the historical situation contained a quiet urgency. Several astronomers knew that the first secure determination of stellar parallax would carry immense significance. The effect had resisted astronomy for generations. Whoever measured it convincingly would close one of the oldest open loops in the history of Earth's motion. Henderson's role in this story is especially revealing because it shows how difficult scientific priority can be when the evidence itself is almost too slight to bear. During his time at the Cape in the early 1830s, he gathered observations of Alpha Centauri that later proved strongly suggestive of parallax, yet he hesitated. Part of that hesitation seems to have come from caution, part from the difficulty of reducing the observations and convincing himself that the effect was real rather than instrumental or methodological error. He returned to Britain before fully publishing the result. This delay mattered. In the history of science, caution can be intellectually admirable and professionally costly at the same time. Henderson had good reason to be careful. The effect everyone sought was precisely the kind of thing an astronomer might imagine seeing before it was truly secure. That problem lay at the heart of the entire enterprise. To observe a tiny annual shift is one thing. To persuade oneself, and then others, that the shift is genuinely due to Earth's changing position in orbit is another. The 19th century had inherited from earlier astronomy a hard-earned awareness of error. Bradley's aberration had shown that annual effects in stellar positions could have causes other than simple parallax. Instrumental imperfections could mimic motion, refraction, temperature changes, micrometer errors, and subtle reductions in calculation could all produce misleading patterns. No serious astronomer wanted to be remembered as the one who had announced the long-awaited proof and then watched it dissolve under scrutiny. The smaller the effect, the greater the moral demand for self-discipline. Bessel's great achievement in 1838 was therefore not merely that he obtained a number, it was that he obtained one carefully enough and defended it convincingly enough that the astronomical world could begin to accept it. His measured parallax for 61 Cygni was small, far less than an arcsecond, but unmistakable within the structure of his observations. The effect meant that 61 Cygni lay at a tremendous distance, yet still close enough, astronomically speaking, for Earth's orbit to produce a measurable change in its apparent position over the year. The very thing earlier observers had failed to find was there after all. The stars had been shifting all along. Human instruments and methods had simply not been ready to catch them. There is something wonderfully restrained about Bessel's triumph. It did not transform the sky visually for ordinary observers. Nobody looking up from a field or city street would suddenly notice the stars wandering because Earth moved. The great confirmation arrived as a number in a scientific paper, an effect extracted through technique, comparison, and reduction. In a sense, that is precisely why it matters. One of the most consequential truths in the history of thought was not delivered through spectacle, but through the patient conquest of minuteness. The geometry that had haunted the Copernican debate for centuries finally became measurable only when science learned to trust what lay beneath ordinary perception. Struve's work also deserves its place in this chapter. He announced a parallax for Vega around the same period, and although later values and methods refined the numbers, his efforts formed part of the same threshold moment. The important thing historically is not simply who crossed the finish line first in some abstract race. It is that by the late 1830s, the astronomical world had reached a level of precision at which stellar parallax could be repeatedly, credibly pursued. The invisible had become measurable. Different observatories, different targets, and different methods were converging toward the same larger truth. The old challenge no longer stood as a theoretical possibility. It had entered the domain of observed fact. Henderson, too, eventually published his results for Alpha Centauri, and in hindsight, his observations likely contained one of the earliest genuine detections of stellar parallax. There is a poignancy in that. He had, in a sense, touched the truth and then drawn back long enough for Bessel to secure the greater historical recognition. But that hesitation should not be treated merely as personal misfortune. It reveals the ethical difficulty of science at high precision. Discovery is not only about seeing, it is about knowing when one has seen enough to speak. Henderson's delay, Bessel's discipline, Struve's parallel work. Together they show that proof at this level is not a single moment of insight. It is a culture of rigor. And beyond the personalities lies the deeper transformation. Once stellar parallax had been measured, the heavens themselves had answered one of the oldest objections to Earth's motion in the exact form that objection had taken. Earth's orbital path was no longer something inferred only from the elegance of Copernicus. The telescopic damage to the old cosmos, the laws of Kepler, the mechanics of Newton, or even the annual displacement of aberration. It was now written directly into the slight apparent shift of nearby stars against more distant ones. The observer moved. Therefore, the stars appeared to move. The geometry had closed. At the same time, the measurement of parallax did something subtler and perhaps even more wondrous. It converted the unimaginable distances once demanded by heliocentrism from a desperate-sounding speculation into quantifiable reality. The stars truly were astonishingly far away. The absence of parallax to earlier generations had not been a sign that Earth stood still. It had been a sign that the cosmos was larger than those generations could yet measure. One can feel the emotional reversal hidden in that fact. The very objection that once empowered anti-Copernican resistance ended by revealing the sheer scale of the universe that heliocentrism required. The silence of the stars had been vastness, not contradiction. This also changed the human place in the cosmos in a way that is easy to understate. The Earth had already lost the center in theoretical and physical terms. But parallax gave that displacement a different intimacy. It was one thing to accept, intellectually, that Earth was a planet circling the sun. It was another to measure the almost imperceptible consequences of that motion against a stellar backdrop so remote that even Earth's orbit became a tiny baseline. The result was humbling in a very specific way. Human beings had not simply moved the Earth from the center. They had discovered that even the scale of planetary motion, enormous to everyday thought, was almost negligible in relation to the depth of the stellar world. For the long history of proof, though, the most satisfying feature of parallax was its directness. There had always been many routes toward conviction. The old fixed Earth had been eroded by elegance, by telescopic discovery, by new mechanics, and by aberration. But parallax answered the original challenge in its own language. It said, with mathematical quietness, that the observer's position had changed because the Earth had changed its position in space. That was what critics had asked to see. At last, it had been seen. Yet even here, the story retains its characteristic restraint. The measured parallax of a star is a scientific victory. But it is not a public revelation in the way later demonstrations could become. It belongs to observatories, calculations, comparison stars, and instruments finely adjusted by expert hands. Its power is immense, but its drama is hidden inside procedure. To most people, the Earth still feels still. The stars still seem fixed. The profound truth has been secured, but it remains secured within the subtle language of astronomy. And that is why one final step still has a kind of beauty waiting in it. After all the centuries of argument, all the invisible measurements, all the delicate shifts extracted from the sky, there would be a moment when the motion of Earth, or at least one part of it, would be made almost physically present before ordinary observers, no longer only in a telescope, nor only in a column of figures, but in a simple moving plane traced out within a public space. And so, after all the calculations, all the altered heavens, all the delicate measurements drawn from stars almost too distant to imagine, the story arrives somewhere unexpectedly near. Not in the depths of space this time, but inside a building. In 1851, in Paris, a heavy metal sphere was suspended from a long wire and set gently into motion beneath the dome of the Pantheon. To anyone entering the space without knowing what they were meant to see, the pendulum might have seemed almost austere in its simplicity. A weight, a cable, a slow sweep back and forth through the air. There were no planets in view, no telescope pointed upward, no pages of geometric reductions spread across a desk. And yet this quiet apparatus would do something the history of astronomy had taken centuries to approach. It would allow ordinary observers to watch the Earth's rotation reveal itself in the room around them. There is something deeply fitting in that shift. For so long, Earth's motion had belonged to the realm of inference. One had to trust the order of planetary paths, or the logic of mechanics, or the subtle behavior of starlight, or the minute displacement of remote suns against the background of deeper space. All of these were powerful, all were real, but they remained, for most people, distant in one way or another. The Earth still felt still, even after Copernicus, Galileo, Kepler, Newton, Bradley, Bessel, and the others had done their work. The body standing on the ground continued to report the same old certainty. The world beneath one's feet did not seem to move. Foucault's pendulum did not erase that sensation, but it did something almost as profound. It created a setting in which stillness itself began to look deceptive in public. Léon Foucault was not primarily an astronomer in the classical sense. He was a French physicist and experimenter, gifted in the art of making physical principles visible. That talent matters here, because the pendulum belongs to a particular kind of scientific beauty. It is not a discovery extracted from a wilderness of data, nor a theoretical unification expressed in abstract law. It is a demonstration, one of the finest ever made, because it translates a vast truth into a motion simple enough to watch unfold. Foucault had already worked on the speed of light and other physical problems, and he possessed a characteristic 19th century experimental elegance. He understood how to let nature show itself with minimal ornament. The principle of the pendulum is often described as though the pendulum's plane of swing rotates. In a deeper sense, What rotates is the earth beneath it. If a pendulum is set swinging freely, its plane of motion tends to remain fixed relative to inertial space. But the surface of the earth is not inertial in that way. It is turning as the hours pass. The floor beneath the pendulum changes its orientation relative to the swing. To an observer standing in the room, the line traced by the pendulum seems slowly to rotate. The effect is not an illusion in any trivial sense. It is the visible consequence of the fact that the observer and the building belong to a rotating planet, while the pendulum's motion tries, as nearly as possible, to preserve its original plane. This idea can feel abstract until one slows down enough to inhabit the scene. Imagine the pendulum released. At first, it sweeps across the same path, back and forth, through the still interior air. Each arc resembles the last, yet gradually, quietly, the line of that motion seems to drift across the floor. Markers placed in a circle beneath it begin to fall one by one as the bob brushes them aside. Nothing in the pendulum itself appears to announce a cosmic truth. It simply keeps swinging, and that is precisely where the force of the demonstration lies. The earth is not shown to turn through violence or upheaval. It is shown to turn through patience. The building rotates unnoticed. The pendulum remains faithful to its plane. The world gives itself away by changing around what seems unchanged. There is a long philosophical echo in that, since the beginning of this documentary, the stillness of Earth has been one of the deepest facts of human experience. To move that Earth, intellectually, required generations of argument and observation. Now, at last, a single instrument made it possible to watch the old certainty loosen in real time. The pendulum did not produce a feeling of acceleration. It did not make the body sense the planet's spin directly. Instead, it taught observers to distrust the meaning of rest. That lesson had been gathering for centuries. Foucault condensed it into a room. His first important pendulum experiment came earlier in 1851, with a shorter setup in the Meridian Room of the Paris Observatory. But it was the public installation in the Pantheon that gave the demonstration its lasting symbolic power. There, beneath that monumental interior, the pendulum became more than a laboratory instrument. It became a civic revelation. Visitors could stand inside a public building and watch a trace of planetary motion unfold before them. In earlier centuries, the truth of Earth's movement had often lived among scholars, within observatories, books, universities, and technical disputes. Foucault's pendulum brought one part of that truth out into a broader cultural space. It allowed the motion of the Earth to enter the architecture of modern public life. The effect also had a geographical subtlety that made it even more beautiful. The apparent rate at which the plane of swing turns depends on latitude. At the poles, the full rotation would be most direct, completing a circuit relative to the ground in about 24 hours. At the equator, in the idealized case, the effect vanishes. At places in between, the rate depends on the sign of the latitude. This means the pendulum does not simply work in one generic way everywhere. It reveals a rotating Earth with local texture. Paris does not show the same turning rhythm as the North Pole would, nor the same as a city nearer the equator. The experiment belongs to the globe as a whole, and the globe enters the room through mathematics made visible. That relation between place and proof is quietly profound. The old fixed Earth had once seemed to offer a universal stability from which the heavens were judged. Foucault's pendulum reverses that emotional arrangement. The local room, the local floor, the local city are no longer neutral stages. They are carried by a rotating planet. and their very latitude shapes the behavior of the demonstration. One begins to feel, perhaps for the first time in a truly embodied way, that human places are not still containers placed beneath a moving sky. They are points on a turning world. Geography itself becomes kinematic. It is worth pausing here to notice a distinction that the history of this documentary has slowly prepared us to appreciate. Earth has more than one important motion. It rotates on its axis, producing the daily cycle of rising and setting. It also revolves around the sun over the course of a year. These motions have different evidential histories. Foucault's pendulum is especially powerful because it addresses the daily rotation directly. The pendulum does not prove the yearly orbit around the sun in the way stellar aberration or parallax do. Instead, it gives visible form to the axial spin of the planet itself, in a story often compressed into the phrase "Earth moves." That distinction matters. The truth was not secured through one argument or one kind of motion. Different aspects of Earth's mobility emerged through different routes, each answering a different layer of the old stillness. That layered history is one reason the pendulum feels so satisfying near the end of this journey. Copernicus had made the moving Earth thinkable by reorganizing the cosmos. Galileo had broken the visual calm of the old heavens. Tycho's heirs and other anti-Copernicans had forced the new astronomy to confront its weaknesses honestly. Kepler and Newton had made celestial motion physically intelligible. Bradley had found direct evidence of Earth's orbital motion by following an annual stellar effect no one had expected in that form. Bessel, Henderson, and Struve had finally measured the parallax that earlier generations could only demand or deny. Foucault did something different from all of them. He let the Earth move before witnesses, and yet even that phrase should be handled with care, because the elegance of the pendulum lies partly in what it does not do. It does not make the planet shake beneath the feet of observers. It does not deliver a crude sensation of spinning, the kind of bodily proof common sense always expected and never received. The Earth continues to rotate with the same serene indifference it had always maintained. The pendulum simply provides a reference against which the hidden motion becomes legible. In that sense, Foucault's experiment belongs to the same family of thought as the whole documentary. Again and again, the world has not changed. What changed was the human capacity to compare, to measure, to reinterpret what looked obvious. There is something almost tender in the way the pendulum accomplishes this. Many scientific demonstrations impress by force, speed, heat, explosion, or dramatic transformation. Foucault's impresses through duration. One must remain with it. One must watch the repeated sweep, the almost imperceptible drift, the slow toppling of markers, or the changing angle of the path. The proof has tempo. It asks the observer to quiet down enough to notice that the room is changing relative to the motion. This makes it unusually suited to the emotional logic of the Earth's motion story itself. After centuries of hurried dispute and longing for decisive signs, one of the most persuasive public demonstrations asks for something close to patience. That patience has its own philosophical resonance. In the older world, stillness seemed immediate, and certainty belonged to the senses. In the modern world that emerged through this history, certainty often belongs to disciplined observation sustained over time. The pendulum rewards those willing to let the conclusion arrive gradually. In doing so, it teaches a broader lesson about scientific knowledge. Some truths do not announce themselves at the scale of instinct. They become visible only when thought and experiment create the right conditions for perception. Foucault's pendulum is, in that sense, more than a proof of Earth's rotation. It is a proof that human understanding can be educated beyond the first report of the body. By the mid-19th century, of course, Foucault was not overturning a dominant belief in a fixed Earth. The larger scientific world had long since moved beyond that. But history is not made only of first believers and final skeptics. It is also made of moments when a truth changes register. A claim once contested among specialists becomes part of wider cultural experience. A conclusion once supported by technical astronomy becomes visible in museums, public halls, classrooms, and the imaginative life of educated society. Foucault's pendulum helped Earth's motion make that transition. It translated abstract certainty into an event that could be watched. In doing so, it gave the modern age one of its most graceful emblems. And perhaps that is why the experiment has lingered so powerfully in the cultural memory. Many people who could not explain stellar aberration or calculate parallax could still stand beneath a great pendulum and feel that something profound was being shown to them. The simplicity of the setup hides the centuries compressed inside it. A swinging weight in a building contains the afterlife of Copernicus, Galileo, Kepler, Newton, Bradley, and Bessel. It contains the defeat of the old assumption that the Earth's stillness is self-evident. It contains, too, the maturing of science from speculation and controversy into demonstrations capable of entering public consciousness without losing their rigor. If you imagine the pendulum in motion now, late in the history we have traced, it begins to resemble a kind of final gesture. The bob swings, the line drifts, the Earth turns. The effect is local and immediate, but it belongs to a planetary fact that once required centuries to establish. One almost feels, in that slow change of angle, the closing of a very old net. The missing parallax had once kept the stars silent. The lack of bodily sensation had once kept the ground innocent. The old heavens had once seemed perfect enough to secure the Earth in place. One by one, those protections fell away. Foucault's pendulum does not replace the earlier proofs. It gathers them into a final physical poise. And so the title of this documentary, if heard carefully now, has changed its meaning. The discovery that proved Earth moves was never one isolated event. It was not a single night under the stars, a lone book, one telescope, one law, one measurement, or one demonstration. It was a long sequence in which different minds answered different parts of the same old human resistance. Copernicus displaced the Earth in thought. Galileo made the inherited sky unreliable. Kepler gave the planetary system a truer architecture. Newton made that architecture lawful. Bradley found an annual stellar effect that depended directly on Earth's orbital motion. Bessel and others finally measured the parallax earlier generations had demanded. Foucault let the turning planet speak inside a room. That is the deeper beauty of the story. Science did not reach certainty here by overwhelming the world with one dramatic proof. It arrived by accumulating ways of seeing, each one correcting a different limitation in human experience. The body had said stillness. The sky had seemed to confirm it. Instruments complicated the picture. Mathematics reorganized it. Physics deepened it. Observation refined it. Public experiment finally gave it a visible shape. The truth had been present from the beginning, but it lay hidden beneath the ordinary confidence of standing on solid ground. And once that confidence was transformed, something larger changed with it. The Earth became a world in motion among other moving worlds. Human beings became inhabitants of a planet that turns without asking to be felt. that travels without appearing to depart, that carries whole civilizations through space under a sky once mistaken for evidence of our own central stillness. The discovery was scientific, certainly, but it was also philosophical, even psychological. It taught us that some of the deepest structures of reality remain invisible until we learn how to ask the world better questions, which may be why, even now, the pendulum remains so compelling. It swings through the same air we breathe. It traces a slow truth across the floor, and in that quiet motion, one can still feel the old certainty giving way, not violently, not all at once, but with the calm, patient grace by which the earth had been moving all along. By the end of this story, the question no longer feels quite the same. Earth does move. It turns. It travels. It carries oceans, weather, cities, and generations of human lives through space with a steadiness so complete that motion disguises itself as rest. What once seemed obvious, that the ground is still and the heavens revolve, gave way to something far stranger and far more beautiful. The world had not changed. What changed was the human ability to see beyond first impressions, beyond habit, beyond the comfort of what the body seems to report. There is something quietly profound in that transformation. The discovery that proved Earth moves did more than settle an astronomical dispute. It altered the relationship between human beings and reality itself. It showed that nature does not always present its truths at the scale of ordinary experience. Sometimes the deepest facts are hidden behind limits of sensation, behind the weakness of early instruments, behind ideas that take generations to mature. To discover them, people had to become patient in new ways. They had to measure what could barely be seen, follow anomalies that seemed almost meaningless, and accept that certainty might emerge only through a long accumulation of partial answers. That is part of what makes this history linger in the mind. Science is often imagined as a sequence of brilliant revelations, but just as often it is a discipline of listening carefully enough to hear what the world is saying in a whisper. And perhaps that is the larger reflection this journey leaves behind. However settled our picture of reality may feel today, there may still be truths around us that remain hidden for the same reason Earth's motion once did. Not because they are unreachable, but because they ask for finer questions, better tools, and a deeper patience than we have yet learned to bring.